Buckle up, everybody, because today we're going to try to find our way through the funhouse mirrors that are highest weight categories and stability conditions.
Yeah.
We're going deep on a paper by Alessio, Cipriani, and John Woolf, and I got to say, I'm already feeling a little lost.
It's definitely a challenging one, but that's part of the fun, right?
All right.
We're leaving behind the familiar world of, like, equations and numbers here and diving into a realm where it's all about abstract structures. Imagine trying to understand how a complex machine works.
Okay.
But instead of taking it apart, you're studying the way all the gears and levers move together.
I like that.
That's the essence of highest weight categories, finding elegant ways to understand these really complex mathematical objects.
So instead of nuts and bolts, we've got categories and morphisms. Got it. But where do we even begin? The paper throws around terms like homological recalons and exceptional sequences like it's nobody's business.
Let's start with something a bit simpler. Remember back in linear algebra when we broke down vectors into their simpler components using bases?
Yeah.
It's kind of like that, but way more abstract.
Yeah.
We're looking for the fundamental building blocks of these objects.
Okay, so I see the appeal, but why highest weight? What makes these categories so special?
Now, that's where things get really interesting. Imagine you have the system for ranking objects based on some special property. You can think about it like importance within the category. Highest weight categories have this really neat feature where you have these highest weight objects that sit at the top. And from these, all the other objects can be built in a very specific, controlled way.
So it's like a pyramid, and these highest weight objects are at the very top, kind of dictating the structure of everything below.
Exactly. And the amazing thing is that these highest weight categories, we see them everywhere. They show up in the representation theory of Lie algebras, the study of perverse sheaves.
Well, hold on. Perverse sheaves. I think we're getting a little out of my depth here, even for me.
Haha. No worries. Don't get too caught up on the name for now. The important thing is that these are really interesting mathematical objects that pop up when you're studying geometric spaces. And the amazing thing is that we can use these highest weight categories to help understand them.
Okay, so we've got these highest weight categories lurking in all these different corners of mathematics.
Right.
But how do we even know if we've stumbled across one? The paper mentions all these different criteria.
Right. It's like a detective's toolkit.
Okay.
One of the tools we have is the idea of thin, exact categories. Think of these categories as being super organized. Every object has a specific place, and they all fit together perfectly.
So it's a perfectly organized library where every single book has its designated place.
Exactly. And then we've got quasi-hereditary algebras, and these are special types of algebras that really lend themselves to highest weight categories. They're like blueprints for building these really structured categories.
Okay, so if we're dealing with a quasi-hereditary algebra, we should be on the lookout for a highest weight category.
You got it. But one of the coolest tools we have is this thing called the Grothendieck group.
Okay.
Now, this isn't about a social gathering, but rather capturing how objects in a category are put together from simpler pieces. Like, imagine you have this really complex molecule. The Grothendieck group helps us keep track of the atoms and how they all fit together.
This is like a mathematical inventory system.
Exactly.
Yeah.
And in the paper, they talk about this really clever numerical test that uses the Grothendieck group. It basically checks if certain numerical properties hold, and if they do, it's a good indicator that we might have a highest weight structure. It's like a secret code for unlocking the structure of a category.
This is some real detective work.
Yeah.
But we haven't even talked about stability conditions yet. Where do those fit in?
Yes. Stability conditions, they're like a special lens that helps us rank objects in a category based on their stability. Think of it like a tower of blocks.
Okay.
Some arrangements are much more stable than others, right? Well, it's the same idea in a category. Some objects are just naturally more stable than others, and those are the ones we're really interested in.
So instead of just looking at the objects, we're also looking at how shaky or solid they are within the category.
Exactly. And to navigate through this whole stability thing, we have a tool called the Harder-Narasimhan filtration. It's like we're sifting through a mixture of particles of different sizes. The filtration sorts everything out based on stability, and it really brings that hidden hierarchy to light.
Okay, so we've got all these tools for identifying highest weight categories. But how does this actually work in practice? The paper gets into some pretty interesting examples.
Yeah. And there's one that really shows just how important order and perspective can be. It involves this simple category that can be represented by a quiver with two vertices and arrows going back and forth between them.
Like a mathematical game of ping pong.
Haha, I like that. So imagine we have this rule. Going back and forth along the arrows always brings you right back to where you started. This simple rule defines the category, and what's interesting is that it actually turns out to be a highest weight category.
So even in this really simple setup, we can find these elegant structures.
Exactly. But here's where things get kind of wild. If we tweak the rules of the ping pong game just a bit, let's say going back and forth results in a slightly different endpoint, we end up with a brand new category. But here's the kicker. This new category is isomorphic to the first one.
Hold on, isomorphic. So they're basically like twins, just dressed up differently.
You got it. They have the same objects, the same relationships, but they're just represented in slightly different ways. But get this. This tiny change completely changes the highest weight structure. The original category, it's a highest weight category, no problem. But its twin, not so much.
Wait a minute, how is that even possible? How can two categories be essentially identical but have different properties when it comes to being a highest weight category?
That's the cool part. It all boils down to how we order the simple objects. In the first case, the natural order just works perfectly to give us this nice highest weight structure. But in the second case, it just doesn't line up. It's like trying to solve a jigsaw puzzle. Sometimes you need to turn the pieces around to get them to fit.
So it's not just about the structure itself, but also about our perspective, the order we choose to look at things.
Exactly. And this just goes to show you that these really subtle differences can have a huge impact when it comes to highest weight categories. It's a good reminder that we can't always judge a book by its cover. We need to dig deeper.
I'm really starting to see how much nuance there is here. Another example that caught my attention was the one about recollement, which you described earlier as like dissecting an object into layers. Does this example show how important that layering is for understanding highest weight categories?
Absolutely. This example looks at a category that has this recollement structure, so it can be broken down into those layers. But here's the thing, it's not actually a highest weight category.
So just because something has layers doesn't mean it's automatically a highest weight category.
Right. It's like having all the right ingredients for a cake, but maybe you don't know the recipe. You might end up with something that looks a bit like a cake, but it's not going to have the right texture or taste without the right technique.
So there's a difference between having the layers and having them work together in the right way.
Exactly. It all comes down to the specific properties of the recollement. In this case, even though each layer of the category is like the category of vector spaces, which is pretty simple, the way they're connected just doesn't have that special something that you need for a highest weight category.
So we have these nice simple layers, but the overall structure isn't quite right.
Exactly. And this misalignment shows up in a few key ways. First, the projective objects in the category, which you can think of as building blocks, they don't break down neatly into the standard objects that you'd expect in a highest weight category.
It's like trying to build a Lego castle, but you're missing a few crucial pieces. You can't quite get that perfect structure.
Perfect analogy. And then this lack of good behavior, it also pops up in those numerical tests we talked about. The multiplicities of certain objects, which should have a really specific relationship in a highest weight category, they just don't add up in this case. It's like trying to balance a chemical equation, but the atoms on each side don't match.
So it's like a near miss, almost a highest weight category, but not quite.
Exactly. But these are the kinds of subtle distinctions that make this area of mathematics so exciting. It's not always clear-cut. There are shades of gray, and these examples really help us understand the complexity of highest weight categories.
Speaking of shades of gray, that last example in the paper seems to really shake things up. It challenges some of the common assumptions about highest weight categories, right?
Yeah, that last one is really interesting. It shows how sometimes relying on shortcuts can lead you astray, especially when trying to identify these highest weight categories.
Oh, what kind of shortcuts?
Well, sometimes, instead of analyzing a category directly, mathematicians can look at what you might call its shadow. Each finite-dimensional algebra, which is often the backbone of these categories, has a corresponding monomial algebra. Think of it like a simplified version.
So like a model of a more complex system.
Right. And there's a rule, the Green-Schroll criterion, that helps us determine if that monomial algebra leads to a highest weight category. For a long time, mathematicians thought that if the shadow, that monomial algebra, pointed towards a highest weight structure, then the original algebra had to as well.
So it was a way to avoid the complexity of the original algebra.
Exactly. But this last example, it throws a wrench in that whole idea. It presents a category that's definitely a highest weight category, but its monomial algebra isn't.
Hold on, the shadow doesn't match the object. That's like saying a cookie cutter shaped like a star makes heart-shaped cookies.
Exactly. And that's why this example is so important. It really highlights how important it is to go beyond these shadow algebras. We need better techniques, better ways of understanding these highest weight categories. Sometimes you can't just scratch the surface, you got to go deeper.
Okay, you convinced me. These highest weight categories are full of surprises. But I've got to ask, why does all this even matter? Like, we've been wandering through this mathematical jungle, but what's the big picture? Why should our listeners care about these things?
It's easy to get lost in the weeds with abstract math, right? We get so focused on the beauty and complexity of it all, we forget to take a step back and think about the bigger picture.
Exactly. So help us zoom out here. What's the point of highest weight categories?
The coolest thing about them is their connections. They might seem abstract, but these categories give us a way to understand some really fundamental concepts, and not just in math, even in physics.
Okay, now you've got my attention. Give me the rundown.
Let's take Lie algebras, for example.
Okay.
They're the mathematical structures that describe symmetry.
Okay. And they're super important in physics, especially when you're thinking about the fundamental forces of the universe.
So we're talking about the underlying patterns that govern how particles interact, from tiny atoms all the way up to galaxies.
Exactly. And these highest weight categories, well, they give us this framework for understanding the representations of Lie algebras.
So it's like having the tools to understand the language of symmetry itself.
Right. But it doesn't stop there. Highest weight categories also have these deep connections to other areas of math, like algebraic geometry and topology.
Whoa, full circle. Remember how those examples connected categories to geometric spaces?
Exactly. It all comes together. There are these amazing links between highest weight categories and the way we study shapes. For example, some highest weight categories, they actually live on algebraic varieties, which are just geometric spaces defined by equations.
Wow.
This connection lets us move between algebra and geometry. Like, we can translate ideas between these two different worlds. It's like we're discovering all these secret passageways in the mathematical universe, connecting everything together.
That's a great way to put it. And it's this interconnectedness that makes math such a powerful tool. By exploring these abstract structures, like highest weight categories, we gain insights into so many different fields, and it often leads to unexpected discoveries.
So the next time someone asks, what's the use of all this abstract algebra? We can tell them it's not just about playing around with symbols. It's about unlocking the secrets of the universe, one equation at a time.
Well said. And this paper, it perfectly captures that spirit of exploration, you know? It pushes the boundaries and shows us that there's still so much out there to discover.
It's exciting. It's like they've given us a map and said, go explore. Who knows what other incredible mathematical wonders are waiting for us?
Exactly. There's a whole universe of mathematics out there.
Well, that's all the time we have for today's deep dive into highest weight categories and stability conditions. We hope you've enjoyed exploring these abstract structures with us.
Yeah. Thanks for listening.
Until next time, keep those brains buzzing. All right, deep dive crew, ready to fire up those neurons? Today we're taking a deep dive into highest weight categories. I've got excerpts from Highest Weight Categories and Stability Conditions, a paper by Alessio Cipriani and John Woolf. And let me tell you, this is some pretty dense stuff.
Dense is putting it lightly. Imagine trying to organize a room full of hyperactive puppies, except the puppies are abstract algebraic objects. That's kind of what mathematicians are up against when they're trying to understand the structure of certain categories.
Okay, I'm getting a sense of the challenge here. So where does this paper come in?
Well, this paper gives us two brand new tools to figure out if these unruly categories actually have, some hidden order, if they're what we call highest weight.
Okay, before we get to those tools, can we back up a bit? What exactly do we mean by highest weight categories? It sounds a little niche.
Sure. It might sound a bit obscure, but trust me, it's a concept with some seriously far-reaching implications. Imagine, if you will, that you're a chef trying to understand what makes a complex dish, really sing. You wouldn't just analyze the final product, right?
Right, you'd break it down.
Exactly. You break it down into its individual ingredients, understand how they interact, see if there's like a particular order or structure that gives the dish its unique flavor.
Okay, so far so good. Following the analogy.
So in our case, those ingredients are mathematical objects, right? And the dish is a special kind of category. And a highest weight category, well, it's like a recipe that tells us, hey, if you arrange these ingredients in a specific way, using these particular rules, you'll get this beautiful, predictable structure.
So it's about finding order amidst the chaos.
Bingo. You got it. But before we dive into the specifics of this recipe, let's set the stage a bit. Cipriani and Woolf, they focus on something called Deligne finite categories.
Delignite categories, all right. And those are...
Well, it's kind of like, think of it this way. Imagine you're about to play a game, but the rules are, like, infinitely complex, and the possibilities are endless. Kind of overwhelming, right?
a little bit.
Deligne finite categories are like choosing a game with, just the right amount of structure. Enough to make it interesting, but not so much that it makes your head spin.
So they're like the Goldilocks categories. Not too big, not too small.
Exactly. They have these key properties that make them, particularly well suited for our analysis. For example, they have a finite number of simple objects, which are kind of like the most basic, indivisible building blocks of our category.
So like prime numbers in the world of categories.
You got it. You can't break them down any further.
Okay, we've got our building blocks. What else makes these Deligne finite categories special?
They also have something called projective objects. Think of these as like special lenses that help us study the properties of our simple objects. And then there are injective objects, which kind of do the same thing, but from the opposite direction.
Like having a microscope and a telescope to study our building blocks. Okay, so we've got our well-behaved Deligne finite category. We've got our simple objects and our special lenses. Where do these highest weight categories fit into all of this?
Now we're getting to the good stuff. A highest weight category, it all hinges on two very special types of objects. Standard objects, which we denote with, that's the Greek letter delta, and costandard objects, denoted by Eric, which is called nabla.
So like the VIPs in our mathematical party.
Exactly. But here's the catch. These standard and costandard objects, they aren't just, randomly chosen. They're defined using a specific ordering of those simple objects we talked about.
Oh, wait, so the order we arrange those prime number objects actually matters?
You bet it does. That ordering is absolutely crucial because in a highest weight category, those standard objects, our ers, become our new building blocks. And then we can arrange everything else in the category in a very structured way based on these ers using what we call a good filtration.
A good filtration. Can you elaborate on that a bit?
Okay, imagine you've got, say, a complex structure, like a multi-layered cake. A good filtration is like carefully slicing that cake into its individual layers so you can examine each part separately and understand how they all fit together.
Gotcha. I think I'm starting to get a feel for this, but this still feels very abstract. Why should we care about these highest weight categories? What's the payoff for all this sorting and arranging?
The million-dollar question. And the answer, well, you're about to witness the amazing power of connections. You see, highest weight categories, they pop up in some of the most unexpected places in mathematics, revealing deep links between areas you might think are totally unrelated. Like, for example, let's talk about perverse sheaves. And no, we haven't wandered into a gothic horror novel or anything.
Perverse sheaves. Okay, now that's a name that definitely sounds like it could belong in a mathematical horror story. What are they?
I know, right? The name's a bit intimidating, but they're not as scary as they sound, I promise. Imagine you're studying, say, a geometric shape, but it's got some rough spots, like sharp corners or points.
Okay, I'm picturing it.
So perverse sheaves, they basically give us the tools to understand those rough spots, those singularities, in a way that kind of smooths things out mathematically.
So we're putting on our mathematical gloves to handle those prickly shapes.
That's a great way to put it. And here's the connection to highest weight categories. Sometimes categories of perverse sheaves, they have this special highest weight structure, which means we can use all those organizational principles we were just talking about to understand these geometric objects that might seem kind of chaotic at first glance.
Okay, so we've got a connection to geometry. What other mathematical surprises do highest weight categories have up their sleeves?
How would a link to the world of algebra with representation theory?
Ooh, algebra and geometry teaming up. Now this is getting exciting.
I know, right? So representation theory, it's all about finding ways to represent these abstract algebraic structures like groups in terms of linear transformations, which are much easier to wrap our heads around, to visualize and to work with.
Like translating from a foreign language into one you actually understand.
Exactly. And guess what? Highest weight categories, they're like the stars of the show when it comes to understanding certain types of representations. They're like the Rosetta Stone that unlocks the secrets of these complex algebraic structures.
Okay, I'm convinced. Highest weight categories are like the ultimate multitaskers of the math world, connecting everything. But let's get back to the Cipriani and Woolf paper for a second. They didn't just write this paper to tell us about these amazing connections, right? What was the main goal?
You're right. All those connections are super cool, but they're just the tip of the iceberg. What Cipriani and Woolf really wanted to know was, can we find some practical, like foolproof ways to actually identify highest weight categories in the wild, so to speak?
And what did they find?
Their answer is a resounding yes. They give us not one, but two new methods for doing just that.
Okay, now you've got my attention. Hit me with method number 1.
Method number 1 hinges on something called the growth-endiate group.
Growth-endiate group. That sounds a little intimidating, not going to lie.
It sounds way more complicated than it actually is. It's a very elegant idea. Basically, the growth-endiate group gives us a way to count objects in a category, even when those objects are super abstract. The key here is that we're counting up to equivalence.
Counting up to equivalence. So what does that mean exactly?
Okay, so picture this. You've got a basket of apples and oranges, right? You could count them one by one, or you could group them together and say, I have 2 types of fruit. That's essentially what we're doing with the growth-endiate group. We're grouping together objects that are similar in a certain way and treating them as equivalent.
So it's like we're trying to see the forest for the trees.
Yeah.
Getting a more general overview.
Precisely. And here's the really cool part. Cipriani and Woolf, they derive an equation that has to hold true if we're dealing with a highest weight category. This equation involves the multiplicities of our standard objects, our fories, our costandard objects, our erts, and our projective objects.
Hold on. Back up for a sec. By multiplicities, are we talking about how many times a particular object appears as a factor of another object?
Exactly. It's like, remember how you can break down a number into its prime factors?
Yeah, like 12 is 2 by 2 by 3.
Right. So the multiplicity of a prime factor tells you how many times it appears in the factorization. In the same way, the multiplicities in Cipriani and Woolf's equation, they tell us how these special objects, our O's and projective objects, how they relate to each other.
So it's like we're analyzing the prime factorization of our category to see if it fits the pattern of a highest weight category.
You got it. This equation, it gives us a really powerful numerical test. If the multiplicities of those special objects, they satisfy the equation, then bam, we know we've got ourselves a highest weight category.
I like it. A nice clear-cut test. But you mentioned there were 2 methods. What's the second method all about?
The second method is a little more on the abstract side, but equally elegant, I'd say. It involves the world of stability functions.
Stability functions. Okay, now we're getting really out there. What are those?
I know, it sounds very zen, right? But we're not talking about mathematical meditation, at least not exactly. Think of it this way. Imagine that each object in our category is vibrating at a certain frequency. That's its phase.
So each object is like a tiny little mathematical tuning fork.
I love that analogy. So a stability function is a special kind of function that assigns a phase to every single object in our category. And here's the key. If we can find a stability function where our standard objects, our A's, have these increasing phases and our projective objects, those P's decompose in a very specific way, then we've struck gold. We found ourselves a highest weight category.
So we're looking for this perfect harmonic arrangement of objects, where those standard objects set the tone and everything else falls into place.
What a way to put it. You've got it. And that specific decomposition of the projective objects, that's where things get really interesting. It's like we're piecing together a mathematical jigsaw puzzle, looking for how it all fits together just right.
A mathematical jigsaw puzzle. I like it. So this decomposition, this specific way the projective objects need to break down, what's it called? There's got to be a name for something this important.
You're telling me? Of course there is. It's called the Harder-Narasimhan filtration.
Harder-Narasimhan. Catchy.
Yeah, well, you know how mathematicians are with names, but it's named after the mathematicians who first really dug into these ideas. Basically, it's a way of breaking down objects into their most, I guess you could say, their most stable components.
Stable components, like the bedrock of these mathematical structures.
Exactly. And the beauty of what Cipriani and Woolf are doing here is they show us how all these seemingly abstract concepts, stability functions, Harder-Narasimhan filtrations, highest weight categories, they're all connected. And it's elegant and incredibly powerful.
Okay, this is all very impressive, but I'm ready to see these tools in action. Do Cipriani and Woolf give us some concrete examples in their paper?
Oh, absolutely. And trust me, this is where it gets really good. They dive into several different scenarios, showing us exactly how their methods work. For example, one of the examples they give explores a category that can be visualized using, get this, a simple diagram called a quiver.
A quiver, as in like arrows and...
Yep, arrows and points. This particular quiver is as basic as it gets, just 2 points, or vertices, and 2 arrows connecting them.
2 vertices and 2 arrows. That sounds almost too easy.
I know, right? But don't let its simplicity fool you. This little quiver packs a surprising amount of mathematical punch. See, this example, it can be interpreted as a category of perverse sheaves on this specific geometric object called CP sup 1 sup.
Okay, so those perverse sheaves are back. So we're connecting this simple little quiver to those rough-edged geometric shapes we talked about earlier.
Exactly. And what Cipriani and Woolf show us is that by using their numerical test, remember that equation with the multiplicities.
Right.
And by using their stability function test, we can confirm that this category, the one associated with the quiver, it's a highest weight category.
So they walk us through it step by step, showing how their methods work with a real example.
Yep. And it's super helpful to see it in action. But they don't stop there. They give us some other examples to highlight different things, like they've got another example with the same quiver, but they tweak the setup just a little bit, and guess what? This time, the category isn't a highest weight category.
Wow, so a tiny change can make all the difference. Like swapping out one ingredient in a recipe can totally change the final dish.
Exactly. It shows us just how sensitive these tests are and why it's so important to have them, to really nail down whether or not a category is highest weight.
It's amazing how these really simple examples can reveal such profound things, about how these mathematical structures work.
Absolutely. And Cipriani and Woolf, they don't stop there. They go even deeper, exploring more intricate examples, really showing us how versatile their tools are. They even tie their work back to earlier research on this related concept called Green-Schroll's criterion.
Green-Schroll's criterion. Okay, you're going to have to refresh my memory on that one.
Right. So Green and Schroll, they came up with a way to figure out if a specific kind of algebra, called a monomial algebra, has the right structure to be quasi-hereditary.
Right. Quasi-hereditary. And what were those again?
Quasi-hereditary algebras. Think of them like the well-organized friends of the algebra world, always keeping things neat and tidy. And as we talked about earlier, there's this deep connection between quasi-hereditary algebras and highest weight categories.
Right. Like two sides of the same coin.
Exactly. So Green-Schroll's criterion, it's like a shortcut to tell if those algebras are as organized as we need them to be.
Got it. A shortcut for checking the sock drawer. Makes sense.
And what's interesting here is that Cipriani and Woolf, they actually show us that sometimes there can be this disconnect between a category and its monomial algebra. They have one example where the category itself, IS, a highest weight category, but its associated monomial algebra isn't.
Interesting. It's like finding this amazing cake that doesn't actually follow the recipe. A happy accident.
Totally. A happy mathematical accident.
Yeah.
And it just goes to show that even in this world of, seemingly rigid rules and structures, there's always room for surprises.
Well, this whole deep dive has been full of surprises. We've gone from herding abstract cats to uncovering hidden connections between geometry, algebra, and even a little topology. I don't know about you, but I'm ready to go explore some highest weight categories on my own.
Me too. Cipriani and Woolf's paper is a great place to start for anyone who wants to dive in. It really highlights the creativity and ingenuity that goes into making sense of these really abstract mathematical concepts.
Well said. Huge thanks to Alessio Cipriani and John Woolf for giving us so much to think about. And to our listeners, until next time, keep those minds sharp and stay curious, deep divers. Welcome to the Deep Dive. Today we're really getting into some hardcore math, I'd say. With this paper, it's all about highest weight categories and stability conditions. And you've really been digging deep into this one. So
absolutely. It's an exciting area. Yeah, we're going to see how these categories kind of bring a sense of order to what can seem like the abstract wilderness of representation theory, and even beyond that.
I love that. Abstract wilderness. That's a good one. I'm all about taming that wilderness with a bit of structure. So the paper, it kicks off with Deligne finite categories, right?
Yeah.
What is it about these categories that makes them such a good fit for this exploration?
Well, think of Deligne finite categories like that sweet spot, that Goldilocks zone for this kind of math. They've got enough structure there to be interesting, but they're not overwhelmingly complex. What we're zeroing in on is categories where you have finitely many simple objects, and they're also Hom and Ext finite.
Okay.
They're Noetherian, Artinian, have enough projectives. Basically, they play nice with certain operations.
Right, so they're well-behaved, relatively speaking.
Yeah, you could say that.
Okay, so we've got the stage set. Now, onto the heart of the matter.
Hmm.
Highest weight categories. The paper describes them as having this kind of inherent hierarchy, almost like a really well-organized library.
Exactly. It's all about the arrangement. In a highest weight category, those objects, they're structured in a very specific way. You could think of it, like you said, organizing books, maybe first by genre, then by author, then by title.
I like that.
And this ranking system, it's not just about tidiness. It lets us take these complicated mathematical objects and break them down
Right.
into more digestible, simpler components. Makes everything a bit easier to grasp.
So it's about imposing order from what could be chaos.
Exactly.
Okay, well, the paper digs into two primary ways to spot these highest weight categories in the wild. We've got the numerical test, and then there are these stability conditions. Let's start with this numerical test. It almost sounds like we're doing some kind of mathematical fingerprint analysis here.
It's a good way to put it, actually. The core of the numerical test lies in something we call the growth NDX group. Essentially, this lets us count objects within a category, but in a very structured, mathematically meaningful way.
Okay.
By analyzing the numerical connections within this group, we can figure out if a category has that special highest weight structure.
So I can't help but think of those crime shows where they're examining blood spatters, looking for clues. But here, our clues are numerical, right?
I like that analogy. And you're right. Just like in forensics, we're on the hunt for patterns, for relationships that tell a story.
Right.
The paper really dives into this interplay between three major players. We've got our standard objects, denoted as Y. Then there are the costandard objects. Those are denoted as y. And lastly, we have our projective covers, denoted as pi.
Okay, so let's break those down a bit. We touched on standard objects before. Those are like the fundamental building blocks.
Right. Exactly. Each simple object, which we denote as psi, has a corresponding standard object, our corollary. You can think of it like this. The standard object is like a designated representative of the simple object. It helps us place it within the grand hierarchy of the category. And then on the flip side, we have the costandard objects, the SI, acting as a kind of counterpart or dual to the standard objects.
So like the yin to the yang of the standard objects.
We could say that.
Okay, and then we've got these projective covers, the pi. They sound like the overachievers of the category in a way.
Laughter. That's one way to think about it. The projective cover of an object is all about efficiency. It maps onto the original object, but without any extraneous information.
So it's like a streamlined, no-frills version of the object.
Exactly.
Okay, so we've got our cast of characters. Let's get back to this numerical test. How do these standard objects, costandard objects, and projective covers come together to tell us whether a category has that coveted highest weight status?
Good question. So the paper lays out these specific numerical conditions that we need to check. The first one zeroes in on the multiplicity of simple objects within the standard objects.
Okay, hold on. Multiplicity. Just a quick refresher. What does that mean in this context?
Right, so multiplicity, it tells us how many times a specific simple object shows up as a part of another object. In a proper highest weight category, the multiplicity of a simple object, our psi, inside its corresponding standard object, the I, should be exactly 1.
Okay, so it's like a one-to-one relationship. Each building block has its designated spot and only one spot.
Exactly. Now, the second part of this numerical test, this is where it gets a bit more involved. We're talking about a specific equation, and this equation connects our projective covers, the pi, to the standard objects, those e's. And this connection is weighted by the multiplicities of the simple objects, the psi's, within those costandard objects, the e's.
Whoa. Okay, that sounds like a mouthful. Can we actually see this equation? I think it'll help wrap our heads around it.
Of course, of course. So the paper states that for a category to earn the highest weight badge, this equation has to hold true. And it is written like this chi-orishizic days.
Okay, I can see why you called it a mouthful. Can you break it down for us?
Absolutely. So first things first, those square brackets, they're important. When you see those like this badge, they're telling us we're working within the growth NDX group. Remember, that's our way of counting the objects. Now that colon in there, the colle, that's how we represent multiplicity. So when you see day, it translates to the multiplicity of the simple objects, say, inside the costandard object.
Gotcha. So we're keeping track of our building blocks, seeing how many of each we need for each object.
Exactly. And this equation, it's essentially a recipe. It tells us how to build a projective cover, pi, using a very specific mix of standard objects, the A, and the quantities of each are determined by the relationship between the simple objects and the costandard objects. It's all about finding that delicate balance.
So to pass this part of the numerical test, a category needs to satisfy this equation for each of its objects.
You got it.
This numerical test is fascinating. It's amazing how we can use math to essentially peer into the very structure of these categories. Now, the paper also mentions these stability conditions as another way to identify a highest weight category. How do those play into all of this?
Well, it's like we're shifting our perspective a bit. Stability conditions give us this whole other lens through which we can view these categories, and by doing that, we gain an even deeper understanding of their internal structure. It's like we're assigning a certain weight to each object, but instead of measuring how heavy something is, we're talking about stability in this more abstract mathematical space.
Okay, so we're going beyond just categorizing objects and starting to rank them based on how stable they are within the structure of the category.
Exactly. We use something called a stability function. This function, it assigns a complex number to every single object. And here's where it gets really interesting. We use the phase of this complex number. Think of it like its angle on the complex plane. That angle, that's what helps us determine the stability of an object.
So we're bringing in complex numbers, we're talking about angles, all to map out the stability landscape of these categories. It's pretty cool.
It is. And the paper makes this argument. If you can find a stability function where all of your standard objects, they're all stable, and their phases, they increase in the specific way as you move up the hierarchy, well, if you find that you're likely looking at a highest weight category.
So the stability function, it's almost like it reveals a hidden order within the category, like a mathematical rhythm or flow.
I like that. That's a really good way to think about it. And what's even more interesting is that often this idea of a stability function existing, it lines up perfectly with those numerical conditions we were talking about earlier. It's like we're looking at the same underlying structure, but from two totally different angles.
It really shows how these different mathematical concepts can kind of intertwine, converge to highlight a deeper truth. Now, I'm really curious to see these concepts in action. The paper mentions some specific examples using quivers and relations. Can we dive into those a little bit?
Absolutely. Those examples are great because they give us this concrete visual way to see how these categories actually work. Remember when we were talking about quivers earlier?
Yeah, you described them as sort of like a mathematical train route with stations and paths.
Exactly. That's a great way to picture it. A quiver, at its core, is a directed graph. Dots connected by arrows. The dots, those represent our objects in the category. And the arrows, those are the morphisms, the ways that we can move between those objects.
Okay, so it's like a roadmap of the relationships between objects. I like it.
Precisely. And then, to add another layer of intrigue, we can introduce relations into our quiver. These relations, they're like rules. They tell us which paths are allowed and which ones are a no-go.
So it's kind of like saying you can get from station A to station B, but you can't go directly from B back to A. You've got to take a detour.
Exactly. And those seemingly simple rules, they have a huge impact on the structure of the entire category. And to illustrate that, the paper gives us a couple of examples. They use a very simple two-vertex quiver.
Okay, so I'm picturing two dots, an arrow between them. Pretty straightforward so far.
Exactly. So in example 6.1, we have this relation that says, the path that goes from vertex 2 to vertex 1 and then back to vertex 2, that's equal to 0. It's like saying you can't just bounce back and forth between those two vertices forever. There's got to be some purpose to your journey.
I like that. There's got to be a reason you're taking that trip.
Right. And when we impose this specific relation, the category we end up with, it turns out, is a highest weight category.
Interesting. But then in example 6.2, we stick with that same two-vertex quiver, but we change the relation. Now, the rule is the path that starts at vertex 1 goes to vertex 2, and then back to 1, that's equal to 0. It seems like a really subtle difference. Does it really change things that much?
It does. It might seem subtle, but even with that small tweak, that new category, it's no longer a highest weight category.
Wow. Really?
Right.
Why is that? It's the same quiver, just slightly different, no back and forth rule.
It all comes down to those standard objects and whether they can still meet those numerical conditions that we talked about. See, in that first example, when the 2, 1, 2 path is 0, all of our standard objects, they fall right in line. Each one has a multiplicity of 1 for its corresponding simple object. It satisfies that crucial requirement.
So everything fits together nice and neatly.
Exactly. But then we switch to the 1, 2, 1 path being 0, and it throws a wrench in the works. One of those standard objects, it ends up with a multiplicity of 2 for its simple object. It breaks that key rule.
It's amazing how such a small change to the relation can have such a big impact on the entire categorical structure.
It really highlights that delicate balance, how even seemingly insignificant changes can ripple outward.
It reminds me of that whole chaos theory thing, the butterfly.
I like that. And speaking of unexpected consequences, the paper gives us another interesting example to consider, example 6.3. They introduce a category, we can call it category B, and it highlights another way that a category might fail that highest weight test. This time it has to do with something called global dimension.
Okay, I'm intrigued. What is global dimension and how does it relate to all of this?
Well, you can think of global dimension as a way of measuring how complex a category is. In the simplest terms, it tells us just how long those chains of morphisms between objects can get. Like, imagine you're trying to get from point A to point B in a city, right? In some cities, it might only take a couple of streets, but then in other cities, you might have to go through this whole maze of winding roads. Global dimension captures that idea, but in the world of categories.
So a higher global dimension means that the relationships between those objects, they can be more convoluted, more tangled.
You got it. And here's the critical part. Highest weight categories, by their very nature, they can't have an infinite global dimension. For things to work out, those relationships have to behave themselves, at least to some degree.
Uh-huh. So even if a category looks like it might be a good fit for being highest weight, if it's got that out-of-control global dimension, it's a deal breaker.
Exactly. And that is precisely what we see with category B. It might have some features that make it seem like a contender at first glance, but then that infinite global dimension, that immediately disqualifies it from being a highest weight category.
It's like the math itself is revealing a flaw, a kind of instability that wouldn't be obvious right away.
Exactly. It's a great example of how these seemingly abstract mathematical tools, they can actually uncover profound truths about the very structure of these categories.
Yeah, it's like we've got this mathematical blacklight that we can shine, and it just reveals these hidden patterns and those inconsistencies that we wouldn't see otherwise.
Yeah.
Now, you mentioned that category B, it also has something called a recollement. What does that mean, and does that have anything to do with why this category can't be highest weight?
That's a great point. So a recollement, it's essentially like taking a category and breaking it down, decomposing it into these smaller, more manageable pieces. Think of it like taking apart a complex machine to understand how all the individual parts work.
So it's all about simplification, making it a bit easier to analyze.
Exactly. But here's the thing. Just because a category has a recollement, it doesn't automatically mean it's going to be a highest weight category.
Okay, so it's not like having all the right ingredients guarantees you're going to bake a delicious cake.
Yeah. Right. You still need the right recipe, the right technique. And in the case of our category B, even though it can be broken down this way, it's those other properties, like that pesky infinite global dimension we talked about. They're the real deal breakers. They prevent it from having that nice, elegant, highest weight structure.
It's a good reminder that math is full of these little nuances, these unexpected twists.
Yeah.
And speaking of twists, there's one more example from the paper that I really wanted to dig into. Example 6.4. This one brings up something called a monomial algebra, and it seems to challenge this common assumption about highest weight categories.
Yeah, this one's a head scratcher for sure. It really highlights that things aren't always as clear-cut as they might appear. But before we get into the thick of it, let's talk about what a monomial algebra actually is. So basically, it's a specific type of algebra that we can represent using those quivers and relations that we were looking at earlier.
Right, so it's like another tool in our toolkit to represent and study those relationships between objects.
Exactly. Now, here's where it gets interesting. There's this idea out there that if you have a category and the monomial algebra associated with it is highest weight, then the category itself must also be highest weight. It makes sense, right?
Yeah, it's like saying if the blueprint for a house is structurally sound, then the actual house that you build from that blueprint is going to be sound too.
Exactly. But example 6.4, it throws a wrench in that whole line of thinking. It presents us with this category that checks all the boxes for a highest weight category. It meets all the criteria, but the monomial algebra associated with this category, it's not highest weight.
Wait, hold on. That's like building a perfectly fine house, but using a blueprint that seems to defy the laws of physics? How is that even possible?
It's a really interesting quirk in the math. And what this example shows us is that these representations, these mappings, they don't always perfectly reflect every single detail of the underlying structure. There can be exceptions, these edge cases, where the tools we're using, they don't quite capture all the complexities of the object we're studying.
It goes to show that math is full of surprises. Now, we've really been in the weeds here talking about all the technical ins and outs of highest weight categories. But I want to zoom out for a second. Why are these categories so important? Where else do they show up in mathematics?
That's the million-dollar question, right? These categories, they're not just some abstract mathematical puzzle. They're actually deeply connected to many different areas of math, and they act as this kind of bridge linking seemingly disparate concepts together.
So they're like a universal language that helps us translate between different mathematical dialects.
I like that analogy. One of the big ones is representation theory. This whole area is about understanding abstract algebraic structures, things like groups, by representing their elements as linear transformations of vector spaces.
Okay, this is bringing me back to linear algebra, matrices,
Sure.
transformations. It's all coming back to me now. So how do these highest weight categories fit into all of that?
They give us a way to classify and understand specific types of representations, the ones with a built-in hierarchy, just like those highest weight categories themselves.
It's all connected. So the same organizing principles that govern those categories, they also underpin certain types of representations, giving us these incredibly powerful tools to study them.
Exactly. And this connection, it's opened up new avenues of research in areas like Lie algebras, which are absolutely crucial for understanding symmetry in both math and physics.
Wow, so we're talking about connections to some of the most fundamental concepts in mathematics and physics. And you mentioned earlier that these categories also have implications for perverse sheaves, which, if I'm being honest, always sounds a bit intimidating.
Yeah, the name's a bit unfortunate. They're really not as scary as they sound. Perverse sheaves are a really powerful way to study geometric spaces, especially those spaces that have singularities or some unusual characteristics.
Okay, so maybe not scary, but definitely complex. So how do these elegant highest weight categories relate to these, shall we say, interesting geometric constructs?
Well, in certain cases, the category of perverse sheaves on a particular space can actually be a highest weight category. That means that all the tools and the techniques we've been talking about, they can be applied to study the geometry of those spaces. But from this whole new angle,
It's like we've discovered this hidden passageway that links together the worlds of algebra and geometry. And suddenly we're seeing these unexpected relationships between shapes and structures.
exactly. And the really exciting thing is this is just the tip of the iceberg. The paper even hints at connections to other areas like Costandard theory, which dives into the really deep end of representation theory.
This is what I love about math. It's like we've been following this trail of mathematical breadcrumbs, and it's led us to this incredibly rich and interconnected web of ideas.
And the best part is we've only just scratched the surface. There's still so much out there to discover, so many unanswered questions about highest weight categories and how they connect to all these different facets of mathematics.
It's humbling and exhilarating to know that even in the world of abstract math, there's always something new to learn, always more to understand. Thanks so much for taking us on this incredible journey.
It's been my pleasure. Until next time.
All right, ready to dive into some seriously abstract math.
Oh yeah, count me in. Always up for a challenge.
Today, we're looking at highest weight categories and stability conditions by Cipriani and Woolf.
Now that's a paper that takes you on a wild ride through some pretty dense territory.
It does, but hey, that's what we're here for, right? To break it down, unpack the jargon, and maybe even have some fun along the way.
Absolutely. Plus, Cipriani and Woolf are working with some really cool ideas here, linking together concepts from Lie algebra representations to category theory.
They really do weave it all together. But okay, let's start at the very beginning. Highest weight categories. Now, I know many of our listeners are already familiar with this concept from their work with Lie algebras.
Right. It's a classic idea in that realm.
But Cipriani and Woolf, they kind of take it to a whole new level of abstraction. They're looking at categories similar to modules over finite-dimensional algebras.
And that shift in perspective, it opens up a whole new world of possibilities.
It really does. But okay, before we get ahead of ourselves, let's rewind a bit. They dedicate a good chunk of the paper to characterizing these highest weight categories, exploring different ways to identify them. They look at 4 established methods, which is really helpful for context, and then they introduce 2 new criteria.
It's like they've given us a whole new toolbox for understanding these structures.
Exactly. So let's start with those 4 established methods, just to lay the groundwork. First up, homological recouplement.
Yes, recouplement. It sounds super complicated, but it's actually a really elegant concept.
It is. So for anyone who's not familiar with it, It's essentially about breaking down a complex category into smaller, more manageable pieces.
It's like taking apart a complex machine, You want to understand how each individual component works so you can figure out how the whole thing functions together.
Divide and conquer.
Exactly. Now, the next method, strictly full exceptional sequences. That one's all about finding those special sequences of objects within the category.
Those sequences, they're kind of like the scaffolding, aren't they? They hold the whole structure together.
Yeah, that's a great way to think about it. They provide the framework, the essential building blocks that define the category's structure.
That's like finding those keystones in an archway. Then we've got thin exact categories. This one always reminds me of archaeology somehow.
Oh, I see that. It's about carefully uncovering those hidden relationships, right?
Exactly. You're looking at these special subcategories, figuring out how they fit together, like piecing together ancient fragments to understand a lost civilization.
And then, last but not least, we have quasi-hereditary algebras.
These guys, they're like old friends, aren't they? Always popping up in the world of highest weight categories.
They are, and they're great indicators. If you see a quasi-hereditary algebra, chances are you're dealing with a highest weight category.
Like a big flashing neon sign. So those are the 4 established methods, but here's where things get really interesting. Cipriani and Woolf, they don't just stop there. They introduce 2 brand new criteria for determining if a category is highest weight.
Right. They're basically giving us new lenses to examine these categories, which is always exciting.
The first one is the numerical criterion.
This one's all about calculations, about finding those precise numerical relationships within the growth endiat group of the category.
So it's a bit like cracking a code, finding the hidden patterns in the numbers.
Exactly. And then there's the stability function criterion. This one's a bit more abstract, maybe even a little bit mind-bending.
It does sound pretty out there. What's the basic idea?
Well, imagine you could assign a sort of phase to each object in the category, represented by a complex number. That's essentially what a stability function does.
Okay, I'm trying to visualize this. So each object gets its own little phase tag.
Precisely. And by analyzing these phases, we can actually determine if the category exhibits those key properties of a highest weight category. They use this idea of Harder-Narasimhan filtrations, which are ways of decomposing objects, to really dig into the stability conditions.
So it's like each criterion is its own unique tool, right? They offer different angles, different ways of approaching the same problem.
Exactly. And the fact that Cipriani and Woolf came up with 2 new ones, it's a testament to their creativity and their deep understanding of this subject.
It's pretty impressive.
Yeah.
But hold on, they don't stop there either, do they? They also revisit some existing work by Green and Schroll, right?
They do. And this is where things get even more intriguing. At least for me, they focus on a specific type of algebra called a monomial algebra.
Monomial algebras. Now, those are fun.
They are. They're kind of like the minimalist painters of the algebra world. They deal with those single-term expressions, no complicated polynomials to worry about.
Each term stands alone, stark and simple.
Exactly. Now, Green and Schroll, they developed a criterion for determining when the module category of a monomial algebra is a highest weight category. But what Cipriani and Woolf do, they actually provide a whole new proof for this criterion using their newly developed numerical criterion.
So it's like they've found a new, more elegant path to the same destination.
Precisely. It's like they've cut through all the clutter and found a more streamlined way to arrive at the same conclusion.
It's always nice to find a shortcut, especially in math. But before we delve into their examples, which, by the way, are super cool, I want to unpack Theorem 4.1 a little bit.
Theorem 4.1. That's the heart of the paper, wouldn't you say?
It really does seem to be the crux of their argument, tying a lot of these ideas together.
It does. It basically says that under certain conditions, being a highest weight category is equivalent to 2 other conditions. It's all about connecting the dots between different perspectives. They start with a really simple example just to illustrate the concepts.
Which is always appreciated, right? It's easy to get lost in the weeds with this stuff.
Oh, absolutely. So they use a quiver with just 2 vertices and 2 arrows between them, one going in each direction. They actually denote it as 5 in the paper, just for reference.
So like a little mathematical boomerang.
Exactly. And this simple quiver, it represents a category with 2 simple objects. Now, depending on the relations you impose on the paths in this quiver, remember, relations dictate how those arrows can be combined. You get different categories, each with its own personality.
It's like the quiver is the basic template, and the relations are the rules of the game.
I like that. A very good analogy. So in their first scenario, they impose the relation that going back and forth along those 2 arrows, it results in a 0 path. It's like saying if you take a round trip, you end up right back where you started, as if you never even left.
A mathematical round trip to nowhere.
Precisely. And this simple setup, with its round trip equals 0 rule, it actually corresponds to a category that behaves beautifully from a highest weight perspective. It's a classic example of a highest weight category.
It's amazing how something so simple can encapsulate such a complex idea.
Right. It's like a little microcosm of the whole theory.
Exactly. And they actually show how this example, it satisfies all the criteria we've talked about, the numerical relationships, the stability functions. It all lines up perfectly. It's like a proof of concept, you know? Little demonstration that everything works as expected.
Exactly. But here's where things get really interesting. In their second example, they keep the same quiver structure, but they flip the script on the relation.
Oh, a plot twist.
Right. Instead of the round trip being 0, they make it so that going in one direction and then immediately back, that results in a 0 path.
So it's like a one-way street now. You can't go back the way you came.
Exactly. And this seemingly small change, it has huge consequences. The category represented by this modified quiver, it's no longer a highest weight category.
Wow, so sensitive. It's like one tiny tweak throws the whole system out of whack.
Precisely. And their criteria, those powerful tools they developed, they can detect this subtle but important shift.
That's what I call precision. Okay, so what about their third example? Do they stick with this quiver-based approach?
They do. But this time, they bring in a new concept. The distinction between a category admitting a recoulement with simple factors and being a highest weight category.
Okay, a recoulement. I'm not going to lie, that one always throws me for a loop.
It's a mouthful, isn't it? But the idea is actually pretty intuitive. In this context, a recoulement is basically a way of gluing together different categories. You're taking these building blocks and seeing if you can assemble them in a way that creates a highest weight category.
Like a mathematical jigsaw puzzle.
Exactly. And what they show in this example is that you can have a category that can be recollected from very simple pieces, categories that are basically just vector spaces, but it might still not be a highest weight category.
So it's like having all the right ingredients but not knowing the recipe.
Perfect analogy. They use a slightly more complex quiver this time, one with 3 vertices, and they show that while it has this recoulement structure, it doesn't quite fit the bill for a highest weight category.
So recoulement alone isn't enough. You need that special something extra.
Exactly. And speaking of special somethings, their final example, it brings in those monomial algebras we talked about earlier.
Oh, right. Those minimalist masterpieces of algebra.
Exactly. And they explore a scenario where you have a category that is a highest weight category, but its corresponding monomial algebra, it isn't.
So it's like the simplified version doesn't quite capture the full picture.
Exactly. It's a reminder that simplification, while sometimes useful, can also mask important details.
It's like trying to judge a book by its cover. Sometimes you got to dig a little deeper.
Absolutely. And on that note, I think it's time we dig a little deeper into Cipriani and Woolf's concluding thoughts. They leave us with some really thought-provoking insights.
So where do they leave us after taking us on this whirlwind tour of highest weight categories?
Well, I think the biggest takeaway is the power of perspective, wouldn't you say? They've shown us how these different viewpoints, the numerical criteria, the stability conditions, those recoulements, they each illuminate a different facet of these complex structures.
It's like having multiple lenses through which to examine the same object, each revealing details the others might miss.
Exactly. And by combining these different perspectives, we gain a much deeper, more holistic understanding of the underlying mathematics.
It's like that old saying, the whole is greater than the sum of its parts.
Absolutely. And Cipriani and Woolf, they've given us a powerful framework for understanding those parts and how they fit together to create that greater whole.
And they've also, I think, given us a renewed appreciation for the beauty and the elegance of category theory.
Oh, absolutely. It's a field that can seem incredibly abstract at first glance.
Okay, maybe not just at first glance. Sometimes it feels like you're staring into the abyss.
Right. It can be a bit daunting, but once you start to see the connections, the way it ties together different areas of mathematics, it's really quite breathtaking.
It's like discovering a hidden map, a secret language that unlocks a whole new world.
Precisely. And Cipriani and Woolf, they're like expert guides on this journey, leading us through the intricate pathways and pointing out the most fascinating landmarks.
Well said. So for any listeners out there who are just starting to explore the world of category theory or who maybe felt a little intimidated by the abstractness of it all.
We encourage you to dive in. Don't be afraid to get your hands dirty with the concepts.
Exactly.
Yeah.
And remember, you don't have to navigate this terrain alone. There are brilliant minds like Cipriani and Woolf who've already blazed a trail. Their work is a testament to the power of mathematical exploration, and we can all learn from their insights.
Absolutely. So let's all raise a metaphorical glass to Cipriani, to Woolf, and to the enduring quest for mathematical truth.
Cheers to that. And a huge thank you to our listeners for joining us on this deep dive. We hope you've enjoyed exploring the fascinating world of highest weight categories with us. Until next time, keep those mathematical minds engaged. Welcome to the Deep Dive. Today we're going deep, and I mean really deep, into the world of highest weight categories. And listen, we know you're no stranger to this stuff. We're operating under the assumption that you, dear listener, are already fluent in the language of representation theory. So, expert speaker, are you ready to unpack this paper by Cipriani and Woolf?
Oh, absolutely. This paper, it's phenomenal, really. It presents a whole new way of looking at how we identify these highest weight categories. They even introduce some tools that could change how we approach other mathematical areas. It's exciting.
Okay, now you've got my attention. You know, I've always been fascinated by highest weight categories. It's like they give us this framework, this blueprint almost, to understand complex mathematical objects.
Exactly, like a blueprint. I like that.
Uh-huh.
And just like a blueprint, there's always something new to discover, right? And that's what Cipriani and Woolf give us in this paper, these new tools, and they're so elegant. But before we get ahead of ourselves, let's set the stage a bit. This deep dive, it's for someone who already knows the terrain, someone comfortable with, say, Deligne and finite categories.
Right. We're assuming our listener isn't fazed by those at all.
Exactly. It's like we're all standing in this well-organized library, no dusty infinite stacks here, and we're about to explore a new section, one that holds those crucial standard objects, the A's.
Ah, yes, the A's. Those are like the cornerstones of our understanding, wouldn't you say? But we know they don't exist in isolation. We have those costandard objects, the Aries A's, and of course, the ever-important projective objects, the pi's.
You're spot on. It's like the placement of those cornerstone books, the A's, they influence the entire layout of the library, wouldn't you say? That interconnectedness, it's key to what we're talking about here.
And it makes me think about all those existing methods we have for identifying these categories. It's like we have all these different maps to navigate this library. Homological recomendments, strictly full exceptional sequences, even those thin exact categories. And let's not forget our trusty quasi-hereditary algebras. Each one offers a unique perspective.
It's true. They're like specialized tools designed for understanding this complex structure. But here's the exciting part. Cipriani and Woolf, they hand us brand new tools in this paper. And that's where this deep dive gets really interesting, at least for me.
Okay, you've definitely piqued my curiosity. New tools, you say. Tell me more about what they are and why our listener who lives and breathes this stuff should be excited.
Well, they give us two completely new criteria for figuring out if something is a highest weight category. And the way they do it, elegant, truly elegant. They lay it all out in Theorem 4.1.
All right, elegant and Theorem 4.1. Now you're speaking my language. But Can you give us a little more? How do these criteria work?
Imagine this. We can sometimes tell if a category has this special highest weight property just by looking at some numbers, some multiplicities in its growth-endiate group. No need to get bogged down in all the categorical details right away.
Wait, hold on. Are you saying we could bypass all that complex stuff and just do some calculations sometimes? It sounds almost too good to be true.
It's not magic, but it is elegant. This first criterion, it all comes down to the relationship between those standard objects, our EIs, the projective objects, pi's, and their multiplicities in the growth-endiate group. Think of it like checking if the library's inventory matches the blueprint's specification.
Okay, I'm following so far. So how does this numerical test actually work in practice?
Their first criterion says a category is a highest weight category if and only if two things are true. First, the multiplicity of a simple object, we'll call it psi, inside its corresponding standard object, EI, that has to be one. It's like each cornerstone is perfectly placed to support one specific part of the whole structure.
So each cornerstone has this unique essential role to play. I like it.
Precisely. And the second part of their criterion, it's an equation, a really beautiful one, actually. It connects those projective objects, the pi's, to the standard and costandard objects that we talked about before. And here it is, pi CA.
Okay, let me just process this equation for a moment. What's the deeper meaning here? What's the connection between the pi's and those EJs and AJs?
Essentially, it tells us that the way those collections, those pi's, are organized, it's fundamentally tied to how the standard objects, the AJs, and those costandard objects, the AJs, all interact.
It's like saying the arrangement of the books in each section has to perfectly complement the way the light falls from the windows, highlighting those special first editions.
Exactly. And the beauty of this numerical criterion is its concreteness. It often gives us this clear, computable way to see if a category has this highest weight property. It's a powerful tool.
I can see why you're so fascinated by this. This numerical criterion, it's already proving incredibly useful. But you mentioned there was a second criterion in Theorem 4.1, right?
Ah, yes. And this one is fascinating too. It takes us into the world of Bridgeland stability conditions, a way of looking at the stability of the objects within our category.
Stability in mathematics always makes me think of tightrope walkers and those perfectly balanced equations. How does this concept play into what we're talking about with highest weight categories?
Okay, imagine our mathematical objects as these, well, sculptures, all delicately balanced to create a sense of wonder. Some parts are naturally stable, like a wide base, while others might be a bit more, shall we say, wobbly.
So some parts of our mathematical structure are just naturally more stable than others.
Exactly. And that's where the stability function comes into play. Think of it as a way of assigning a stability score to each object in our category, represented by a point on the complex plane. The key is in how these points are arranged, their phases.
It's like we're color-coding our mathematical blueprint, with the most stable parts highlighted in bright, reassuring colors.
Now you're getting it. And their second criterion states that a category is a highest weight category if and only if we can find one of these special stability functions where those standard objects, those iris, are stable. And importantly, their stability increases in a specific order.
So not only do those cornerstones need to be solid, but they also need to be arranged in a specific hierarchy of stability.
You got it. And there's one more crucial piece to this magical stability function. It also has to guarantee that the Harder-Narasimhan factors of our projective objects are made up entirely of those stable standard objects. It's a mouthful, but it's like making sure that even when we break down a collection, a pie, into its most basic stable parts, those parts still carry the mark of those cornerstone standard objects.
Wow. It's like we're seeing the same cathedral, but through a different lens, one that highlights the inherent strength and stability of each element.
You're exactly right. And what's remarkable is that both of these criteria, the numerical one and the stability criterion, they're deeply connected. They're two sides of the same coin, each offering unique insights. But to really grasp their power, we need to see them in action. That means diving into the concrete examples Cipriani and Woolf provide in their paper.
Now you're talking. I always love seeing how these theoretical concepts play out in specific situations.
Yeah.
So lead the way. What's the first example we should explore?
Okay, so quivers. Before we get into the specifics of these examples, could you maybe give us a quick refresher on what quivers are and why they matter in this context?
Of course.
Yeah.
Think of a quiver like a network. It has dots, which we call vertices, and arrows connecting them. Each dot, each vertex, it represents a simple object in our category. And those arrows, they show us the relationships between them. They give us this nice visual way to understand how everything fits together.
So it's like a zoomed-in view of our blueprint, showing us those individual building blocks and how they connect.
Precisely. Now, the first two examples in the paper, 6.1 and 6.2, they focus on this really interesting quiver. It has just two vertices, just two dots, with a pair of arrows going between them. It kind of looks like a boomerang, if you can picture that.
A boomerang! Okay, now that's not something I expected to hear today. A boomerang in the land of highest weight categories, who knew? Right, but it illustrates a really important point. See, even in a setup as, well, seemingly simple as this, with a global dimension of 2, meaning the relationships between objects can only get so complex, we can still have a highest weight category. But, and this is important, it all comes down to how those simple objects, those dots on our boomerang, how they're arranged. It's like finding that one specific orientation that allows the boomerang to fly just right.
So even in this simplified model, the order, the arrangement of those building blocks, it matters. I'm starting to see where these new criteria become really helpful.
Exactly. Cipriani and Woolf, they show us how those numerical conditions, those multiplicities we talked about, they act like this precise measuring tool. They can quickly tell us if a particular arrangement gives us a highest weight category or not. And what's really neat is that they show how those stability functions are color-coded blueprints. They back up those numerical findings. It all ties together.
It's like having two different ways to check our work to make sure that mathematical building is structurally sound.
Exactly. And it gets even better. Example 6.3. Now that one's interesting. It delves into this concept called a recombinant that is not homological.
Okay, gotta be honest, that sounds a little intimidating. Can you break that down for me a bit?
Yeah.
What's so special about a non-homological recoulement?
Sure. Think of it this way. Remember how we often expect certain, well, nice properties to hold in our mathematical structures? Well, in this case, those nice properties, they don't quite work the way we might expect them to. It's like, how should I put it? It's like finding a hidden passageway in our library, but instead of leading to a secret room filled with first editions, it just ends abruptly in a wall, a bit of a dead end.
A mathematical dead end, got it.
In a way, yes. And here's where Cipriani and Woolf's work really shines. Even though this category, it might initially look like it could be a highest weight category, there are numerical tests. They quickly reveal its true nature. It's like they've given us this mathematical metal detector, and it's beeping loudly, telling us, nope, this one's not what it seems.
Those criteria are starting to feel less like tools and more like superpowers.
Right. But the real mind bender, at least for me, it comes with example 6.4. This example, it exposes the limitations of a very well-established criterion, one developed by Green and Schroll, and it really pushes the boundaries of our understanding.
Okay, now you've really got my attention. A mind bender, you say. Tell me everything.
So Green and Schroll's criterion, it's super useful, don't get me wrong. It works beautifully in a lot of cases, but it relies heavily on this thing called monomial algebras. Think of them like simplified versions of the algebras we often work with, a bit like using a really basic map to navigate a complex city. And what Cipriani and Woolf do is they present us with this example, this category, and it's definitely a highest weight category, but here's the kicker. It can't be identified using Green and Schroll's method.
It's like trying to use that simplified city map to navigate through a jungle. It just doesn't have the detail you need. So this example, it's showing us that the existing tools, they're not always enough. We need a more powerful approach.
Exactly. Cipriani and Woolf's example, it shows us that their criteria, they can identify these categories even when those old reliable methods fail. It's like they've given us this new, super detailed map, one that can guide us through even the densest mathematical jungles.
This is incredible. I'm so eager to hear more about what this means, what the implications of their findings are.
The implications, oh, they're huge. Cipriani and Woolf haven't just given us new tools, they've opened up this whole new playground for exploration. They've connected highest weight categories and stability conditions in this incredibly elegant way, and it has the potential to, well, really shake things up in a lot of mathematical areas.
This feels like the start of something big.
Yeah.
But we'll have to save that for after the break. We'll be right back to finish up this amazing deep dive, so don't go anywhere. And we're back, ready to dive back into those examples. You're about to walk us through examples 6.1 through 6.4.
Right, yes. So those first two, 6.1 and 6.2, those boomerang quivers, remember how those have just two vertices and the arrows between them?
Oh, absolutely. I'm still picturing boomerangs flying through mathematical space. It's a great visual.
It is. And they illustrate this really crucial point. Even in a category with a global dimension of 2, meaning the relationships between objects are limited in their complexity, we can still find a highest weight category. But, and here's the catch, it all depends on how those simple objects, those dots on our boomerang, how they're arranged.
Like finding that one sweet spot that makes the boomerang fly perfectly straight, right?
You got it. And what's neat is that Cipriani and Woolf, they use their numerical criterion on these boomerang examples, and guess what? They find that the arrangement of those simple objects, those vertices, it directly determines whether or not you get a highest weight category.
So it's like there's this precise combination, this order to the vertices, that unlocks the highest weight property.
Exactly. It's like a lock and key, almost. And what's really cool is that those stability functions, they confirm it. It's like the stability function is saying, see, the numbers are right.
Okay, so we've seen how these tools work in these simpler boomerang cases. But what about when things get more complicated? Like in example 6.3.
Yes, example 6.3. This one throws a bit of a wrench in the works with that whole recoulement that is not homological business.
Right, that dead end we talked about earlier.
Exactly. It's like we're exploring this mathematical structure, and we think we're on the right track, but then boom, we hit a wall. But here's the beauty of Cipriani and Woolf's criteria. They can see through that wall.
So even though this category, it might seem like it could be a highest weight category, their criteria can spot those hidden flaws that rule it out.
Precisely. Their numerical tests, they're like, nope, not this time. It's really quite elegant how they can detect those inconsistencies.
I'm telling you, these criteria are starting to feel like some next-level mathematical magic. But you said that example 6.4, that was the real showstopper.
Oh, example 6.4. Now that one is where things get really interesting. It really highlights the limits of some of our existing tools. Specifically, it shows us where Green and Scholl's criterion, a tool that's been incredibly reliable, well, it shows us where even that can fall short.
I love it when new research pushes the boundaries of what we thought we knew. Tell me more.
So Green and Scholl's criterion, it works wonders in a lot of cases, especially when we're dealing with monomial algebras. But Cipriani and Woolf, they present this example, this category, and it's definitely a highest weight category, but get this Green and Scholl's method, it doesn't pick it up.
It's like having a map that suddenly stops working when you reach a certain point. You know you're in the right spot, but the map just can't keep up.
Exactly. It shows us that there's this whole class of highest weight categories that this well-established method might completely miss. It really underscores the need for new tools, for new ways of looking at these concepts.
And that's where Cipriani and Woolf come in, with their more powerful, more versatile criteria.
Precisely. They've given us a new map, one that can take us further than ever before.
This has been an incredible journey, expert speaker. It's amazing to see how this paper has reshaped our understanding of highest weight categories.
It really has, and I think the key takeaway here is that mathematics is a constantly evolving field. We're always learning, always discovering new connections, new ways of looking at things.
It's a good reminder to never stop questioning, never stop exploring. And on that note, we'll wrap up this deep dive. We hope you enjoyed exploring the fascinating world of highest weight categories with us today. Until next time, keep those minds curious.